The figures below shows a simply supported beam and its cross section. Therefore, we have two figures here. This first figure is a figure that is showing a simply supported beam carrying a uniformly distributed load over the whole of its span. That is a total span of 3.6 meters, a UDL of 7 kilonewtons per meter. The beam is also carrying a point load of 20 kilonewtons at point C. A point load or a concentrated load of 20 kilonewtons. Now the question is, the beam carries a load that is a point load of 20 kilonewtons and its self-weight or the uniformly distributed load is 7 kilonewtons per meter. Calculate the maximum normal stress at the XX section. This second figure here is showing the cross section of the beam, whose cross section is a rectangular section, but the cross section have got a hole, or you can say that the beam is hollow. It has a hole of 15 centimeters diameter. Now, the first thing we are going to do is to locate the center of gravity of this beam section. And we are going to locate it using this table. I'm sure by now we are familiar with this table from our two previous videos that we have done. And if you have not watched them, please go to YouTube, search for Kamiti and watch the videos. Remember to subscribe, to like and to comment. This table is made of 4 columns, or we have 4 columns in this case. The first column is a component. We have 2 components, a rectangle and as well as a circular hole. The next column is for the areas of the 2 components. The third column is centroidal distance y from LL. This is LL. And then the fourth column is AY. That is area times the centroidal distance y. Now, starting with the area, and in this case the area of the rectangle given by breadth times depth. Therefore, the rectangle have got a breadth of 20 centimeters and a depth of 30 centimeters. So 20 times 30, that is 600 centimeters. Therefore, we have an area of 600 centimeters for the rectangle. Circle, the area is going to be pi over 4 d squared. The diameter is 15. Therefore, pi over 4 times 15 squared, that's going to be 176.7 square centimeters. The centroidal distance y from LL for the rectangle, that's going to be half the depth of 30 centimeters, which is 15 centimeters. Therefore, y for the rectangle, that is going to be 15 centimeters. The centroidal distance y from LL for the circular section, from the top surface of the beam to the center of gravity of the circle, which is this point, is 10 centimeters. The remaining distance, that is from the center of gravity to LL, that will be 30 minus 10, which is 20 centimeters. Therefore, we got 20 centimeters there. From there, we calculate AY, that is the area of each component times the centroidal distance y. So for the rectangular section, we are going to have 600, the area, times 15, that is y, which is going to give us 9,000 centimeters raised to the power of 3. And on the other hand, we have 176.7 multiplied by 20, that's going to be 35, 34. So we got 35, 34. So centimeters raised to 3. Now, since this is a hole, we are going to get the difference, or we are going to subtract AY for the rectangular section minus AY for the circular section. And when you subtract 9,000 minus that, the 5, that, the 4, that's going to give us 54.66 centimeters raised to the power of 3. On the other hand, we are also going to subtract the areas of these two components, and here we have 600 minus 176.7, that is going to be 423.3 centimeter squared. Therefore, we have completed our table. From there, for us to be able to determine the position of the center of gravity of this rectangular beam section, we are going to determine bar y, and bar y in this case is the distance from LL up to the center of gravity of this rectangular section. And bar y is usually given by the summation of AY divided by the summation of A. Therefore, the summation of AY 54.66. Therefore, we have 54.66. Divide this by the summation of area, which in this case is 423.3. Therefore, we have 423.3. And when we divide the two, we are going to have 12.9 centimeters. Therefore, that is bar Y. In this case, the distance from LL all the way to the center of gravity of the rectangular section is 15. Therefore, 12.9 is below 15. And in this case, I had predetermined that. So that is the position of the center of gravity of this rectangular beam section. And at the center of gravity, that is why the neutral axis passes. So we have 12.9 centimeters. Now, this section here that is the section from the neutral axis all the way to LL. This is the section that is subjected to tensile stress. Therefore, we call it YT. The remaining section from neutral axis all the way to the upper region of the beam section, that is a section subjected to compressive stress, and we usually call it YC. So YC will be given by the depth of 30 minus 12.9, which in this case is going to be 17.1 centimeters. Therefore, this is the region subjected to compressive stress. So we call it YC. Now, after locating the position of the center of gravity of the rectangular beam section, the next thing we are going to calculate or to determine is the bending moment at this region XX. The reason being, using the bending equation, we are going to have this relation: the bending moment divided by the moment of inertia is equal to stress all over y. So that is the bending equation. Therefore, we are going to calculate the bending moment at section XX. We are also going to calculate the moment of inertia of this rectangular beam section, so that we calculate the stress. Y we already have. We have YT as well as YC. We are going to determine which one we are going to use or to apply in this relation. Now, starting with the bending moment about the XX section, we are going to find that by taking moments about this region or about this section from end B of this simply supported beam. Now, for us to be able to calculate the bending moment about this section, first of all, we have to determine the values of the reactions at support A as well as at support B. Remember, for every action, there must be an equal and opposite reaction. Therefore, we must determine the values of these two reactions. And we are going to begin with the reaction at support B. And in this case, we are going to take moments about end A. Therefore, taking moments about point A, we are going to have the following. So that's going to give us RB times the distance from B to A, which is 3.6 meters. Therefore, we have RB times 3.6. So that is anti-clockwise moment is equals to the following clockwise moments. Remember, the sum of clockwise moments must be equal to the sum of anti-clockwise moments, and that's why we are equating the anti-clockwise moments to the clockwise moments. The clockwise moments are as follows. We have a point load of 20 kilonewtons times the distance from C to A, which is 2.4 meters. Therefore, we have 20 times 2.4 meters. Then we add another clockwise moments because of this uniformly distributed load, and that's going to be given by 7 times. The whole span is 3.6 meters. Therefore, 7 times 3.6 meters. That is now converting this uniformly distributed rod to point rod. And when you convert a UDL to point rod, that point rod usually acts at the center or at the mid span of that whole span. Therefore, it's going to act somewhere at the 1.8 meters point. That is half of the whole span. Therefore, times 3.6, divide this by 2. So this is going to be RB times 3.6 being equal to, when you carry out that calculation, that's going to give you 93.36. So that's what we are going to have. Now for us to get the value of RB, we are going to divide both sides by 3.6. Therefore, 93.36 divided by 3.6, that's going to be 25.93 kilonewtons. Therefore, that is the reaction at support B. On the other hand, the reaction at point A, we are going to apply reaction at A plus reaction at B is equals, or in other words, the sum of upward forces must be equal to the sum of downward acting forces. So we are going to have the sum of downward forces. We have a point load of 20 kilonewtons plus the UDL of 7 kilonewtons per meter. So 7 kilonewtons times a span of 3.6 to convert the UDL to point load. This is RB. So RA plus RB is equals 20 plus 7 times 3.6. Therefore, the reaction at A plus the reaction at B, which is 25.93 kilonewtons, that's going to be equal to 45.2. So 20 plus 7 times 3.6 is equivalent to 45.2. So the reaction at A is going to be 45.2 minus 25.93, which is going to be 19.27 kilonewtons. Therefore, that is the reaction at support A. So we write here reaction at B being equal to 25.93 kilonewtons. 25.93 kilonewtons. At support A, we have 19.27 being the reaction at A. So 19.27 kilonewtons. Now, after getting the values of the reactions at both supports, the next thing we are now going to determine is the bending moment at section XX. Now, taking moments about XX, the bending moments at X will be given by reaction at B, that is 25.93 times the distance from B all the way to XX, which is 2.4 meters. Therefore, mx, that will be 25.93 times 2.4 meters minus, that is an anti-clockwise moment, minus the following clockwise moment, 20 times the distance from C to XX, which is 1.2 meters. Therefore, you have 20 times 1.2 meters minus, between B and XX we have a UDL of 7 kilonewtons per meter. Therefore, that is going to be 7 kilonewtons per meter times a span of 2.4 meters. So that is converting the UDL to point load, which we rank at the midpoint of B and XX, which in this case is 2.4 divided by 2, definitely at this point C. Therefore, 2.4, we divide that by 2. Now, mx will be given by, when you solve all that, we are going to have 18.072 kilonewtons. Therefore, that is the bending moment at XX. Now, after getting the bending moments, the next thing is to calculate the value of the moment of inertia of this rectangular beam section. Now, For us to get or for us to determine the value of the moment of inertia about the neutral axis, we are going to calculate the moment of inertia of the rectangular section about the neutral axis, and we subtract that with the moment of inertia of the circular section about the same neutral axis. Now, the moment of inertia of the rectangular section about the neutral axis will be given by the breadth of the rectangle multiplied by its depth cubed divided by 12 plus its area into the size of this elemental strip here. That is the distance from the center of gravity of the whole section to the center of gravity of this rectangular section, which in this case is going to be y minus yt. Therefore, we are going to have y minus yt, and then we got that squared. Therefore, the breadth of the rectangular section is 20 centimeters. So we are going to have 20 centimeters times its depth, 30 centimeters cubed. Divide this by 12 plus the area of the rectangular section is 600 square millimeters. Therefore, 600 square millimeters into y for the rectangular section is 15, or half of 30. Therefore, you have 15 centimeters minus yt, which is 12.9, or in other words, bar y, 12.9 centimeters, and then that one is going to be squared. Now, when we carry out this calculation, that is going to give us 47,646 centimeters raised to the power of 4. So that is the moment of inertia about the neutral axis of the rectangular section. Now, for the circular section, the moment of inertia about the neutral axis is going to be given by pi over 64 d raised to 4. That is the formula of calculating the moment of inertia of a circular section, plus the area of the circular section into. So the distance from the center of gravity of this whole cross-section of the beam to the center of gravity of the circle will be given by yc, which is 17.1 minus 10. Therefore, that's going to be yc minus 10, and then we got that squared. Now, this will lead us to pi over 64. Therefore, we got pi over 64 times the diameter of the circle, 15 centimeters. Therefore, 15 raised to the power of 4 plus the area of the circle, 176.7 square centimeters. So 176.7 square centimeters into yc is 17.1 centimeters minus 10 centimeters, and then we square that. So when we carry out our calculation, that's going to give us 11,393. So having that, we can now determine the moment of inertia about the neutral axis of this rectangular cross section of the beam, and that's going to be the moment of inertia of the rectangular section, which is 47,646 minus that one for the circle 11,393. So when we find the difference between the two, that is going to be 36,253 centimeters raised to the power of 4. Therefore, that is the moment of inertia of this rectangular cross section of our beam. Therefore, the next thing we are going to do is to calculate the maximum normal stress at section XX. And for us to do that, we are going to use the bending equation, which is given by this relation. So we have the bending moment divided by the moment of inertia is equals to stress divided by y. Therefore, we have the bending moment. Here it is, 18.072 kilonewtons. We have the moment of inertia about the neutral axis of this I-beam section. We got it there. We have y, that is YC, 17.1. So we are going to make stress the subject of this formula. And therefore, stress is going to be given by the bending moment about the XX section multiplied by YC on the compressive section, divide this by the moment of inertia about the neutral axis of this rectangular beam section. Therefore, this is going to be the bending moment 18.072 kilonewtons. We have to convert it to, or we can convert it to newtons by multiplying that by 1,000. Therefore, 18.072 times 1,000 newtons. Then we multiply that by YC, which is 17.1 centimeters. We have to convert that 17.1 centimeters to meters, and that is going to be 17.1 divided by 100 times 10 raised to the power of -2. Then we divide all this by the moment of inertia about the neutral axis, which is 36,253 times 10 raised to the power of -8. Therefore, the normal stress at section XX will be 8.52 times 10 raised to the power of 6 newtons per square meter. Therefore, that is the stress in newtons per square meter. We have to leave this to SI units, 8.52 mn, that is mega newtons per square meter. So that is the value of the normal stress. So we are through with our question. Just have to thank you for following our channel and watching our content. Please don't forget to subscribe and to hit the notification bell as well, so that you'll be the first person to be notified every time we post a new video. So thank you so very much.